Welcome everybody to my presentation on artificial intelligence, specifically on machine learning and learning paradigms. Let's get started, everybody. All right, so let's begin today with machine learning. So as we've already covered, machine learning, or sometimes abbreviated to ML, is a subset of the field of artificial intelligence. It uses statistical algorithms that learn from data to make predictions without explicit instructions by finding patterns in that data. Machine learning is an iterative process, meaning it works in a loop, repeating parts of the process continually to improve over time. As we've also seen, machine learning is the larger subset of artificial intelligence that deep learning has as a subset of machine learning, which we will examine in our next lesson. Machine learning uses several models to implement the learning that we will examine as well. In traditional programming, for AI, the code was written with specific rules of programming, such that when users provided the input data, the computer would provide a specific answer as the output data. However, a paradigm shift in artificial intelligence now towards machine learning operates under the following. For data input, lots and lots of training data, like thousands of pictures of cats, is inputted as training input data. The answers input are the labels that are put on the data, saying that this picture is labeled, this is a cat and this is not a cat. And then the rules is the output. The machine learning creates the rules, or it creates its own learning model that determines if the image is a cat or not a cat. This paradigm shift was crucial, as before the shift, AI often hit a complexity wall. Traditional AI couldn't manually code enough rules to handle the messiness of the real world. By treating the rules as the output rather than as the input, machine learning unlocked the ability to handle tasks where the rules are too nuanced for any human to write down all those specifics. Machine learning can be explained in various ways that are step by step, including methods previously seen. The data comes in to an algorithm. The pattern is recognized and identified through the algorithm. The model creates or modifies itself. The model makes predictions and decisions, and then the model gets feedback and refines itself back iteratively back to the input phase. Or we could consider machine learning a life cycle where we address a problem. We collect data input and data preparation. The machine learning model is selected to use this data, and then the model is trained. The model evaluates itself through that iterative process. And finally, we deploy the model, which then brings us back to more data input, more preparing of the data in preparation, and evaluating whether or not that model is effective. We could also look at it in phases. So in machine learning, phase one is problem definition and data preparation. So what are we looking at here? Well, step one, we have to figure out what problem that this machine learning model is going to address. And what that means is we're going to translate the needs of that problem into a machine learning task. We want to improve user experience and predict the needs of the user in step one. In step two, we prepare the data. This is a cleaning process. So what happens when we have missing values in our data? How do we remove the outliers and the duplicates from our data? We talk about feature engineering. We extract and format the relevant data, or transform raw data like text and images into numerical data that computers can handle. We split the data, into a training set. So that would be the majority of the data is in a training set, and then a testing set that we hold back from training to evaluate how well the training actually performed. Then in phase two, selection and training, we select a model. We match the model to the type of data that our problem has identified. We then perform the training loop during step two. We feed the training data into the algorithm. We measure how much error that the model has performed, essentially what you could call a loss function. How much error, how much is it off? We optimize the model using algorithms to affect the model's internal parameters, which, as we will learn later, are called weights and biases. And then we continually repeat this process, identifying patterns and continually improving the model. In phase 3, evaluation and deployment, this is the reality check, right? We're going to test the model now on unseen data, not the data we trained with, but data that it hasn't seen before. We use certain metrics to measure whether or not it's been successful: the precision, the accuracy, the recall. And then we deploy the model. We integrate the model into the real world application of the problem. This is often done through something called an API, an application programming interface. We continually monitor the model for what can be called model drift, which is where the model degrades over time. And we automate the retraining of the model so it learns to train itself automatically. So it's important that you grasp that machine learning with all those details. What's important is that you grasp that machine learning is a step-by-step cycle. It's not a once and done process. It is an iterative phase that shifted away from the traditional programming model with its rules and instead uses this continual learning cycle to continually learn rules from the data that it trains with and the specific sets of data. And in the next section, we're going to examine those data sets and the 3 big paradigms of that learning data: supervised, unsupervised, and reinforcement learning in machine learning models. All right, so let's move to that phase now. Let's start taking a look at these learning paradigms. We've already touched on the ways that machine learning uses data in its learning paradigm, and those are being considered the 3 pillars of learning. So let's look at each one. Supervised learning. Well, that's where we take data and put a label on it. So for example, if we're feeding a model a bunch of images of, say, cats and dogs, we would label the images. This is a cat, this is a dog. But as well, during supervised learning, the mechanism of this process is it will learn by matching the input data, the label that's on the data, to the output. So if it identifies a cat, the label will match up. So it's like having the answer key to a test. We answer the test and then we check the answer key. Did we get it right? That's supervised learning. Now we shift over to unsupervised learning. For this type of data, there are no labels. So now we have pictures of cats and dogs, but in no way are they identified as cats and dogs. They are unlabeled. Now, with this mechanism, we're going to be looking for patterns. We're going to be looking for structures, for similarities, for correlations. So the training model will examine what kind of patterns, like, ooh, look, this happens to be an animal and it has ears and it has a tail. Is it a cat? Is it a dog? It's going to look for patterns because there's no label on the data to identify what it is. Finally, in reinforcement learning, this is where there's a certain state of the learning and there's an action that is associated with it. So this is a traditional style of learning, which is trial and error, where there's a reward, potentially even a penalty for getting it right or wrong. So we want to maximize the reward. We want to try and get it right more than we get it wrong. So reinforcement learning rewards the model for getting it right over time. So using these programmed algorithms to analyze the large data sets, whether supervised, unsupervised, or reinforcement learning, the AI machine learning model will start to find patterns. It will start to make decisions and perform and improve its performance over time. Now, with supervised learning, we can compare this to like a student learning from an answer key to a quiz. This AI learning paradigm uses that labeled data. So each input has a paired output, the expected output, the label that tells you what the answer is, sometimes called an input-output pair. This data and the model itself learns to map the input to the correct output by minimizing the error between its prediction and the label of the correct answer. In supervised learning, the type of output you're trying to predict generally falls into one of 2 categories. A classification. So for example, we're training a model to classify things into, say, groups or buckets or categories. For example, it can look at data like emails and determine, is this a spam email? Is this not a spam email? In my example with the pictures, is this a cat versus not a cat, or is this a cat versus is this a dog? The other type of model that we're looking at here is a regression model. This is forecasting a continuous numerical value, basically like a percentage. Instead of a category, it will predict a quantity, for example, a stock price or a temperature or the value of a home, or like I said, a percentage. It's trying to predict a numerical value as accurately as possible. And again, the goal is to minimize the amount of error taking place, or the loss function. The divergence between what we predicted in the model and what the labeled truth of the data is. So did it predict the cat correctly and it's labeled cat? Did it predict the stock price correctly compared to what the stock price actually is? With unsupervised learning, we're going to be training a model on that unlabeled data. So there is no answer key here. We're letting the model discover the patterns within the data, discover the structures, discover the relationships on its own without giving it an answer key, without giving it a label. This is essentially the AI model playing a detective. It's learning to cluster the things that are similar. So as it looks through all the pictures, as it looks through all the emails, it tries to find those patterns and put them into clusters or into categories. It doesn't have an answer to go with. It's looking at the patterns of the data itself without being told what the right outcome looks like. In unsupervised learning, it generally takes on tasks like clustering. What clustering means is it's going to group the similar data points based on proximity. So a good example is if we put it on a traditional graph, right? You can see in that picture there that the circles that are close together or clustered together in proximity, meaning they're close together, would mean that they're probably in a similar grouping, right? Like for example, like this is the purchasing behavior of a store customers. So certain customers only purchase a certain item or only purchase at a certain type of day. So they cluster together based on their commonality. Then there's anomaly detection. So looking for those outliers. So you can see in this graph, there are two circles that are outside of the cluster, right? These are those rare occasions, those data points that deviate significantly from the normal data, okay, of an unlabeled data set. For example, if we're looking at fraud, credit card fraud, or maybe a certain piece of equipment fails on rare occasions, those would be outliers or anomalies that the model is looking to generally look for. And then there's what's called dimensionality reduction, which is simplifying complex data into simpler data, but preserving the characteristics. So this is common with images, right? Images are very complex in terms of the amount of data in the image itself. For example, if you see in this image, the image of a three-dimensional cube. So in other words, we're kind of compressing it and flattening it out so that we can turn that complex data into somewhat simpler data, but still maintain all of its properties and all of its characteristics. Now we turn to reinforcement learning. This is where we train an agent or an AI model to make decisions by rewarding it for good behavior and penalizing it for bad behavior or actions within a controlled environment. Over time, that AI agent obviously is going to learn through that trial and error with that positive and negative feedback to continuously refine its performance towards the positive or towards the optimal strategy to maximize the reward over time. But this is cumulative, right? This isn't just a once and done. This is within that iterative process. It's going to continually shape itself to keep getting better and better. So this approach you can see is often used in, say, for example, robotics, or in video game development and game playing, or autonomous agencies like self-driving cars. They're going to make mistakes. Over time, with reinforcement learning, we want to keep reducing that mistake, rewarding good behavior, and sort of penalizing the bad behavior. All right, let's take a quick look at a video showing a real-world application of reinforcement learning.
AlphaGo Zero is the strongest Go program in the world. It outperformed all previous versions of AlphaGo. Specifically, it defeated the version of AlphaGo that won against the world champion Lee Sedol, and it beat that version of AlphaGo by 100 games to 0. So all previous versions of AlphaGo started by training from human data. And they were told, well, in this position, the human expert played this particular move, and in this other position, the human expert played here. AlphaGo Zero doesn't use any human data whatsoever. Instead, what it has to do is learn for itself completely from self-play. So the reason that playing against itself enables it to do so much better than using strong human data is that, first of all, AlphaGo always has an opponent of just the right level. So it starts off extremely naive. It starts off with completely random play. And yet, at every step of the learning process, it has an opponent, a sparring partner, if you like, that's exactly calibrated to its current level of performance. And to begin with, these players are very, very weak, but over time, they become progressively stronger and stronger and stronger. People tend to assume that machine learning is all about big data and massive amounts of computation. But actually, what we saw in AlphaGo Zero is that algorithms matter much more than either compute or data availability. In fact, in AlphaGo Zero, we use more than an order of magnitude less computation than we used in previous versions of AlphaGo, and yet it was able to perform at a much higher level due to using much more principled algorithms than we had before. I think I can speak for the team by saying that we were all pleasantly surprised by just how far it went, that eventually it was able to surpass all of our expectations, and it was able to actually climb up the ratings until after around 40 days, we found that it had actually defeated all previous versions of AlphaGo to become the strongest Go program in the world. And this is all for a system that's been trained completely from scratch, starting from random behavior and progressing from first principles to really discover tabula rasa how to play the game of Go.
Okay, so having seen machine learning and having seen the examples of these learning paradigms, we need to be aware of potential issues. For example, algorithmic bias. This is where models digitize and amplify the historical prejudices that are hidden within training data. I mean, training data comes from us, the humans. So we have bias, and then we pass that bias on through our historical data into the models. Minorities, marginalized groups are often disproportionately impacted by this training data. We can also have what's called overfitting and hallucinations. Models can learn the wrong lessons. They can, for example, conclude that all brown patches on an image are horses, or confidently generate false information, a hallucination that they confidently present as true. Perhaps that shows that with responsible AI, we cannot omit the so-called human in the loop of this learning process to really verify this data and the results. All right, everybody, thank you so much for watching this presentation, and I hope you have a great day.